Hi guys, so in this video I'll talk about disjoint set union data structure. I mean, it is one of my favorite data structures and I'll try to explain it in the best possible way. I will talk about what DSUs are, what kind of problems it can be used to solve, their applications, and I will also provide you an object-oriented code implementation of DSU, which I think is much better as compared to all those raw implementation out there on internet, because OOPS implementation is much more extensible and flexible, and it is much more clean as well. I mean, it produces much clean code. So after watching this video, I mean, you will not need to study DSU from any other resource. I mean, I'll try to cover all the possible things in it, all the efficient implementations and all that, and I will also solve a lead code problem. So let's jump into it. So like, let's imagine a scenario where there are 7 people. Okay, so here I am representing those 7 people as 1 2 3 4 5 6 7. So these are being represented as individual disjoint sets, and these arrows are representing that the parent pointers. So we'll come to it later that why parent pointers are important and like what is their significance, but currently the element itself is the parent. Okay, so like one's parent is 1 itself, two's parent is 2 itself, and so on. So I come and I tell you that, hey, 1 and 2 are friends, 3 and 4 are friends, and 5 and 6 are friends. So to model this relationship in DSU, we'll do something like this, that we will actually modify the parent pointers of the elements. So I make the parent of 2 as 1. I mean, I could have done it the reverse way as well. I could have made the parent of 1 as 2. I mean, there's nothing wrong in it, but for this case, we have made 1 as the parent of 2, and 1's parent will remain 1 itself. Similarly, I merged 3 and 4. I did the union of 3 and 4. I made 3 as the parent of 4, and similarly, union of 5 and 6. I made parent of 6 as 5. Okay, and then so if you look at this group, so here for this group 1 and 2, the representative of this group is 1. So representative is the element who is the basically whose parent is that element itself. Okay, so similarly, representative of this group is 3, and representative of this group is 5, and representative of this group is 7 itself. So again, we'll see what is the significance of representative, but they are pretty important in DSUs. So I come again and I tell you that, hey, 4 and 2 are also friends. So to merge these two groups, what we do is that we find the representative of 2. So 2's, we go to parent of 2, that is 1, then we go to parent of 1, that is 1 itself, so 1 is the representative. Similarly, to find the representative of 4, we go to the parent of 4, which is 3, we go to the parent of 3, which is 3 itself, so 3 is the representative. Then we merge these two. So here I have modeled that relationship, like I made the parent of 3 as 1. I could have again done it the reverse way as well, that I could have made parent of 1 as 3, but this is the way I did it. So now you can see there are 3 total groups. One group is this, one group is this, and one group is this. So this gives us a lot of information. Like, one information is that how many elements are there in each group. Like, this group has 4 elements, 4 people, this group has 2 people, this group has one person, and we know the representatives of each group. And apart from that, we can also answer queries like, hey, is 2 and 4 connected in any way? So to find that, we find the representative of 2 and we find the representative of 4, and we check if they are both are same, then they are connected, otherwise they are not connected. So representative of 2 is 1, and representative of 4, like we go to the parent of 4 3, we go to the parent of 3 1, and 1's parent is 1, so that is also 1. So these are connected. If I ask you, hey, 4 and 7, are they connected? So we find the representative of 4, which is 1, and 7's representative is 7, so they are both different, so they are not connected. So these are the kind of problems which DSU can be used to solve. Like, so let's jump into the, so before jumping into the implementation, like let's try to see a couple of things here. Like one of this is, so DSU basically has 2 principles, path compressions and union by rank. So let's first talk about union by rank. So let's say that there are these 2 groups. One group is this and one group is this. This group's representative is 1 and this group's representative is 3. Okay, I tell you that, hey, 2 and 5 are friends. So you will union these 2 groups. Okay, so you will find the representative of 2, which is 1. You will find the representative of 5, which is 3, and then you will union them. Now you have 2 choices, whether to make 1 as the representative of this new group or 3 as the representative of this new group, right? So union by rank says that for efficiency purposes, that element becomes to be the representative of the new group, which has more basically elements in its current group. So like 1 has only 2 elements in its current group and 3 has 3 elements. So 3 has more elements. So hence 3 should be the representative of new group. So what we would do is that we would remove this link and we would make 1's parent as 3. Okay. And similarly, there is another thing called path compression. So let's look at what path compression is. So let's look at this scenario. I tell you that find the representative of 5. So for finding the representative of 5 in the code or in the algorithmic way, what we will do is that we will use recursion. Like we will keep on going to the parent of 5. Like we'll keep on basically jumping on the parents till we find an element whose parent is that element itself. Like from 5 we'll go to 4. Now 4's parent is 3. From 3 we will go to 2. 2's parent. Then we'll go to 2's parent, which is 1. Then we'll check 1's parent. So 1's parent is 1 itself. Okay, so we have find the representative. Now when this recursion stack will unwind, so at that moment we make some changes. Like this will unwind in this way. It will come to 2. Then it will come to 3. So when we are at 3, what we would do is that we would basically remove this link and make the parent of 3 as 1 directly. That is the representative itself. Again, we go to 4. Like when the recursion stack unwinds further, we are here at 4. We again remove 4's link and make parent of 4 as 1 directly. Similarly, we remove this link for 5 and we make the parent of 5 as 1 directly. Okay, so why did we do this and how it will help us? So it will help us in this way that when we wanted to find the representative of 5, it took us 5 hops currently, right? Like I had to go from 5 to 4, 4 to 3, so on until I reached 1. But when second time or any further time when someone will query the representative of 5, he will need to make only 1 hop. So this way we reduce the time complexity or the number of hops required for finding the representative. So this is what we call path compression. We compress the path of length 5 to only a path of length 1. So this was all about disjoint set union. So let's look at the implementation of it, how we can efficiently implement this disjoint set union, union by rank and path compression. So here I have written a C++ implementation. So here is this class DSU. Okay, so it has these 2 private data members, which are the rank array and the parent array. So rank array will basically help us in doing the union and parent will represent the parent pointers. Okay, so rank will basically represent how many number of elements are there in that group. So this is the constructor of DSU. Like we take the number of elements initially, we initialize the rank and parent array. So rank array we have initialized of length n plus 1 because like array and DC start from 0, and currently each element's rank is 1 because there is only like each element is in its independent group and there are only 1 element in each group. Similarly, parent array is initialized and I make the parent of like every element's parent is that element itself. If you remember this first image, so here like every element was the parent of itself. Okay, so here we have initialized our data structures. Now let's look at the find method. So find method is simple. You want to find the representative of element x. If you first check if parent of x is x itself. If that is the case, then you return this because this is the representative of this group. Else we basically try to find the parent representative recursively. So we call the find method with parent x as the argument. And as I told you, for path compression purposes, we will basically override the parent of x as the representative itself. Okay, so this is how we do the path compression, how we take care of path compression, the thing which we did here while we unwinded the recursion stack. So finds implementation is pretty easy. Let's see union by rank. So you are given 2 elements a and b and you want to merge them or union them or basically put them in the same group. So you first find the representative of a, you find the representative of b, then you check if they are already in the same group. Like if a representative of a and b, if they are same, then they are already in the same group. You do not do anything, you return early, and this check is very important, otherwise it will mess up your whole data structure. Now for doing union, we use the rank principle. We check which representative has more elements. So if rank a is greater than rank b, then we make the new a as the representative of new group. So that's what I did. I made the parent of B as A, and I incremented the rank of A. Like rank of A will be incremented by the number of elements which were present in the group B. Else we make B as the parent of A and we increment B's rank, and it will be incremented by the number of elements present in the group A. So if you see here that rank of each representative basically determines that how many elements are there in that particular group. Okay, so this is like the efficient implementation of DSU and pretty clean and object-oriented code. So let's look at it, how we'll use it. So here is the main function. We initialize DSU with 7 elements. Okay, so here we have called the constructor, and then we do a union by rank, like we did in the what we did here in this image, that 1 and 2 were friends, 3 and 4 were friends, and 5 and 6 were friends. So that is what I have done here. 1, 2, 3, 4, and 5, 6. I have unioned them, and then 2 and 3 were also friends here, right? So that's what I have done here. I did a union of all. So now we are checking this, like how many elements are in group 1, in group 5, and group 7. Okay, so group 1 is this, whose representative is 1. There are 4 elements. In 5 there are only 2, and in 7 there is only 1. So this should print 4 to 1, and we are checking if whether 2 and 4 are connected. So they are connected because they are same representative. So yes, and we are checking if 7 and 4 are connected. So this should return no. Okay, so let me also show you the code for num connections and are connected method. We already saw the code for union by rank. So num connections is doing nothing. It is just returning the rank of the representative of this particular element, because the rank of representative basically tells you the number of people or the number of elements in that group, and are connected can be found by using this. If representative are same, then it means they are connected, otherwise they are not connected. Okay, so I already have the output of this program generated here on IDE1. So you can see here that people in group 1 are 4, in group 5 are 2, and group 7 are 1 only, and 2 and 4 connected return yes, and 7 and 4 connected return no. So this is as expected. So let's try to quickly solve a lead code problem as well, which uses DSU. So this is the problem, number of provinces, problem number 547. The problem is simple, like it tells you that there are n cities, and like some of them are connected, and if city A is connected with city B and city B is connected with city C, then we say that city A is indirectly connected with city C. Okay, like that's what we did in our example as well. And we say that a province is a group of directly or indirectly connected cities and no other cities outside of the group. So if you check with this, basically compare it with this example. So here you can say this is one province where 1, 2, 3, 4 cities are there in this province 1. This is another province where 5 and 6 are there, and this is another province. So there are total 3 provinces. Okay, and so basically you are given this is connected matrix. Is connected ij represents that city I and is connected ij is equal to 1 represents that city I and city j are directly connected, and 0 represents that they are not directly connected, and you have to return the total number of provinces. So like in this example, the total number of provinces are 3. So it's pretty easy to solve using DSU. What we do here is my DSU implementation. I mean, it is same what I showed you earlier. Okay, the find and union by rank methods, and this is the method which we need to implement. So this is connected 2-dimensional matrix we are receiving as an argument. So we first check if this is connected array. Basically matrix is empty, basically if there are no cities, and if they are empty then we return 0. Otherwise we find the number of cities. So size of his connected matrix will give you the number of cities. We create a DSU with n number of cities. Then we iterate over each element of is connected, and we check if ij is equal to 1. That means if they are directly connected, then we do a union by rank. Okay, we merge those 2 cities, and eventually we have to find how many groups are there. So finding in this group, to determine that there are 3 groups, what we can do is that like the groups or the provinces are equal to the number of representatives. Okay, like there are only 3 representatives, 1, 5, and 7. So all you need to do is you need to iterate over all the cities, and you need to check whose basically whose parent is the same as that element itself. You need to basically find the number of representatives. So that is pretty easy to do. I iterate over all elements, I find the representative of each element, and I check if the representative is equal to the element itself. So this means that So this means that that is the representative of the group, and we increment the count because the number of representatives is equal to the number of these disjoint sets or the number of provinces. Okay, so that's why we call this data structure disjoint sets as well, like it is representing these 3 disjoint sets which are equal to the number of provinces in our case, and we eventually return this count. So I hope you guys understood this. So as a homework, you should try to solve more problems of DSUs, and you should actually also try to see what is the time and space complexity of this data structure. Like space complexity is pretty simple, it's ON, because we are using only these 2 arrays, and the size of the arrays is equal to the number of elements initially present. Time complexity is a bit interesting. So you should do this as a homework because that will also enhance your understanding about this data structure. So I hope you guys liked this video. So thank you guys for watching. Please don't forget to like, subscribe and comment, and I'll see you all next time.